In part 4 of section 10, we're going to discuss the notion of a matrix equation. You're familiar with equations when you're dealing with just real numbers and variables that represent real numbers. But here we're going to see equations written so that way the variables represent a matrix, an unknown matrix for that matter. Now, as it turns out, many of the usual properties of real numbers will extend to matrices. I say many because not all of them do. As far as we're concerned, we are only focusing on three operations: the sum of two matrices, the difference of two matrices, and then a scalar product where it's a real number times a matrix. All of those are going to have the usual properties of real numbers. So for our intents and purposes, that will be true. Example 10.5 is going to give us two matrices. We have a matrix A as well as a matrix B, and we are being asked to solve each matrix equation for X. So if I think of this as just a typical solving situation and I'm being asked to solve for X, look at part A. It says X minus B is equal to A. Then I would just add B to both sides of the equation, getting it to cancel on the left, resulting in the statement X equals A plus B. So X represents the unknown matrix that we're trying to solve for, but X is being defined here as the sum of A and B. Since we know what A and B are, we should be able to perform this operation and then actually calculate what X needs to be represented as. So then X is going to be 4, 5, negative 3, 2, added with 1, 0, negative 1, 2. So I write down the elements that are representing A and B, and now I just go through the addition like we did on example 10.4, adding the corresponding elements together. So starting with the first row, first column, 4 plus 1 to get 5. Go to the next column, first row, that'll be 5 plus 0 to get 5. And then dropping to the second row, first column, negative 3 plus negative 1 to get negative 4. And then finally, second row, second column, 2 plus 2 will give us 4. And then this represents the unknown matrix X that is going to be the solution of this equation. Now it is also possible to check. So if I wanted to check, let me put that back there. So to check this, I would want to take the original statement, which is X minus B is equal to A, and I'm going to substitute in what we just calculated for X. So that would be 5, 5, negative 4, 4, minus B is 1, 0, negative 1, 2, and that's supposed to be equal to matrix A, 4, 5, negative 3, 2. So if we can show that this is a true statement, that means that our solution for X is correct. So on the left-hand side, I'm supposed to combine the two matrices with subtraction. 5 minus 1 will be 4. 5 minus 0 will still be 5. Negative 4 minus negative 1 will be negative 3. And then 4 minus 2 will give me 2, which ends up matching exactly what I'm expecting to get. So I have my true statement that verifies that my solution is correct. So you can always go back and take your solution and plug it back in. I've encouraged you to do that all semester long. That doesn't change here. So for part B, we have a slightly more complex looking matrix equation, but still it's just a matter of using your basic solving techniques to get X isolated by itself. I would start with subtracting 5A. So then we would have 2x is equal to b, and I should make that a capital X because it's supposed to be a matrix, not just a single real number, 2x is going to equal b minus 5a. And then should probably divide both sides by 2 next, so that way I can get the x completely isolated. So if I divide both sides by 2, this will then say matrix x will be b minus 5a all divided by 2. So we should now substitute in for b and a, since we know what those matrices are. And once we get the representation of the entries for B and A actually in the statement here, we have to make sure that we perform the correct order of operations. I'm going to start with the scalar multiplication of 5. So I'm going to just distribute the 5, leaving the subtraction as an operation for me to perform next. So I'm going to copy down matrix B, and then I'm going to come up with the representation that I need for 5a. So 5 times a is really going to be 20, 25, negative 15, and 10. And that all needs to be divided by 2 still. So now I want to perform the subtraction with the b and the 5a matrix. And that should result in just a single matrix. Let's see, 1 minus 20, negative 19. 0 minus 25 is negative 25. Negative 1 minus negative 15 will be positive 14. And then finally 2 minus 10 to get negative 8. So all of that is divided then by 2. So with division by 2 like this, we can think of that as being equivalent to multiplication by the reciprocal. Because I didn't really tell you in the definition that you could divide by a scalar. I just said that you could multiply. Now in reality you can, but to make it match exactly what the definition says, I should think of it like this. 1/2 times this matrix. And that is 100% equivalent to saying take the matrix and divide it by 2. Multiplying by 1/2 does the exact same thing. So if I do that, then I should be able to get to my final result for matrix X. That's going to be negative 19 halves, negative 25 halves, 7, and negative 4. And I'll go ahead and box that in as the final answer. And you should check by plugging this back into the original equation to verify that it does in fact work.